Thank you, sir. Good morning, dear respectful audiences. My name is Umut Demirezen. I'm from the Udemy INC. I'm an engineering manager working as a machine learning department in the machine learning department. Today, I want to explain a little novel big data system, which is called Lambda architecture for processing very huge amount of data, both at the same time and both at the real time and the data in rest architecture. So a little bit background. I want to give you a little bit context about it. What is big data? In this data, we can learn here lots of different sources, but the most simplistic definition. Big data is not only consist of the huge amount of data. The data comes from the different sources and different formats, and also by using the classical data processing tools, for example, databases or MATLAB, this kind of programs maybe is not enough to process a huge amount of data. Comes from different sources with different speeds. So this makes us to use another different kind of technologies. So we can define the big data. For 5 years ago, we will have a rule of 4 V's: volume, variety, velocity, and veracity. In these days, we can define a big data with 7 or 10 V's because we see lots of different kind of features of the data, and we have to adapt it ourselves. Volume, as you know, data at scale, we have very big huge amount of data, and comes from the variety of the variety of many forms: unstructured, structured text, sound, video, and velocity. We can define this as data in motion. Data is generated as some source and transferred to another place with different speeds. For example, when you click a Facebook or LinkedIn like button, it generates this kind of information from your browser to send their servers. And veracity. All data contains lots of uncertainties, and you should model this uncertainty to predict more desirable results. In the literature, there are 4 types of data exist in these days, but the most common ones are data at rest. When you generate a data, put it some database on some place, and it lives until you delete it, or it stays in that. You can process data where it's saved. The second one is data in motion. When the data processed or generated from one source to another part, you can transfer data by transferring. On the transferring stage, you can process the data and apply some rules. You can calculate some analytics, or you can train your machine learning algorithm also. This can be defined as data in motion. These are the very common data types in these days, especially in the industry, we can take care of. Linked data is another type of data. Data has some contextual or relational link between them. For example, I'm your friend, you are my another friends. This kind of chain can be improved by one by. Another one, most important one maybe, the time series data. It is direct related to Internet of Things or sensor data. This is a very important type of data in these days. But unfortunately, in our current technology, we have to use different kind of big data technologies to process this data. It is not effective way to use the big data technology for specialized to processing time series data, apply it to the data at rest, and vice versa. This is not a good way. So, as a quick summary, I think animations are gone. No problem. When you get data, the first thing you applied is extract transform and load (ETL) process. You convert different kind of sources as a one common format or several formats that you can process, and you can convert that data. You may convert that data from data at rest, or when you save data at rest, you can arrange some agent, arrange a program to directly process data where it lives. According to the architecture, according to the literature, the first part of the literature until 2009, we always focused on the batch processing. Batch processing is good. We can scale your data processing algorithms. High performance computation can be possible, but it takes so much computation power and it takes so much time to finish or get the results. The second part of the literature or industrial solutions directly focus on the real-time processing. You can process data where it generated and completely process the data and obtain the results while you transfer the data. This is very good way to process data because you have a speed, access to data and calculate and get the results very fast. But it is very hard because transmission lines or your data comes very repetitive manner, transmission lines broke or this kind of handicaps are very common for the industrial processes. You will get definitely wrong answers to your questions. But after 2020, there is a good improvement, and we can call it as third generation. This is the hybrid processing. We try to process both data at rest and data in motion at the same time. But these requires different kind of technologies working in cooperation with the processing of the data. This will be the most important thing in these days for the high performance computing and parallel computation. There is a limitation which can be explained by the CAP theorem. According to CAP theorem says reveals that a shared data system can only choose at most 2 of 3 properties: consistency, availability, and tolerance to the partitions. This theorem says you will always have 3 of 2 most important abstracts for the data processing. Your data processing can be consistent and available. You can reach and consistently process your data, or your data system can be available and fault tolerant, but cannot be at that time your system cannot be consistently answer your questions. So this theorem is very important, but we can defeat these inaccuracies, inconsistencies by using the Lambda architecture. Lambda architectures are, I will show the details a little bit later, but Lambda architectures most important properties are robustness, fault tolerance, low latency read and write, scalable, generalization. You can apply every part of problem by using the Lambda architectures. Extensive, it can support ad hoc queries, and it requires minimum maintenance, and you can easily debug your algorithms by using the Lambda architectures. The general Lambda architecture consists of 3 parts. First, you receive a data from a data bus, and you will have a speed layer which constructs your real-time processing of the data. That layer completely specialized for data in motion part of the data. The second part is the batch layer. This layer directly consists of the batch processing type of the data. In coordination with the batch layer and speed layer's work, your results are generated and sent to the serving layer, the third layer, just specialized for high performance output, high performance support for high performance queries. The idea is simple, but implementation and usage is much more hard because you need a very strict control and coordination between these layers. I will show you later. When you get a query, for example, calculate me a mean value or variance of any analytics data, this query just receive an answer, receive a response from the speed layer because it is incoming. We have a receiving the incoming data and it calculates very fast. But at that time, some real-time transmission may occur, but this directly causes a defect at the results. But also, however, using the batch layer, we can launch a job, launch a computation step, and work for that part of the data and update the real-time data and show the real queries. This is different kind of query results merged in the serving layer and that give the response of the query. There are lots of different big data technologies. I will show you later. But the earlier times, we generally, or every industrial processes use Kafka as a data bus, Apache Storm, which is also open source project, just specialized for the working on the real-time data, Hadoop as a batch processing layer, and any serving layer, for example, Druid database or even SQL databases are possible. All data will be served by using the return part. It will be served in the real-time views. The earliest part of the data will be served in the batch views. A serving layer joins these two views and gives a very strict results. So we applied this technology stack to a real-time air and ground surveillance problem, which is very critical. How can I explain in plain English? During the flight, every plane, every air vehicle has to broadcast a signal, which is very easy to analyze and easy to obtainable. You can get these signals from their transponders by using a $5 cost USB sticks. I will show you a little bit later. Which is called a software-defined radio. Just debugging, just decrypting the code and send it from an Apache cluster or a big data cluster. When the air traffic is so much around that area, receiving and also one aircraft sends nearly 100 messages in a second. It will be huge data transmission, and you are passively listening in the air from during this passage. So when the air traffic is so hard, so dense, this kind of problem, we measured that this kind of Lambda architecture can be applicable this problem and measure its success. So we receive. I will come back later. First, let me explain the ADSB, how it works. It is automatic dependent surveillance broadcast system. It's mainly when a plane receives a current location from the GNSS or satellites or GPS, sends this message and also other kind of message. For example, its fuel rate, its code number, which airline it belongs, which company it belongs, passenger numbers, or this kind of very valuable information. It directly broadcasts around another plane or the ground station or the satellite. It can be automatically recoverable and receivable around the world or a limited range of the world. In the future, they are trying to remove the radar dependency, but using this technology. It is also some kind of cybersecurity related issues, because you can also broadcast this kind of signal to the air, and you can fake the air traffic controls or other air vehicles that can see another air vehicle comes toward it. This kind of stuff is possible. And also it is currently used in the airports to detect any obstacles, stable obstacles, and other moving tracks, for example, buses or the baggage vehicles. By using this information, you can develop an algorithm, and also you can develop this kind of algorithm to prevent collision. Very busy airports and also air and the ground is also consist of producing lots of data, and you should analyze it very quickly and inform the pilots or air traffic control or everywhere very quickly. So we use this technology to this problem. Currently, maybe everyone knows flight radar 24 is currently use another kind of technology. Their sensors all located all around the world, and if they don't receive any information for a while, 2 minutes or 3 minutes, it directly predicts the current air vehicle's trajectory by using the older values of it, just doing a kind of animation. But this is a very good approach to develop this kind of technology. So we select very good, very novel, not novel, very new technologies. For example, batch processing, we use Apache Spark and Speed for Apache Streaming, serving layer Apache Druid, and data bus Apache Kafka, and we develop very strict control and coordination application. Because this is a big data system, it works on tens of clusters, tens of computers. You cannot easily put a debug point and debug your algorithm, because you don't know which algorithm sent to do what part of the cluster, and you will not have a chance to debug the algorithm in a distributed way. So we got some different kind of technology stack. We call it using the same coding architecture, so same coding for different layer approach. It provides a novelty because when you develop a software for the processing the data, you should develop speed layer part of technology with a different source code, and also you should develop a batch layer with a different source code. For example, you can use C++ for the speed layer or C# for the batch layer. But when any improvement or any update required, you should use two different technologies and update two different technologies. It's not a good way because you cannot extensively debug this kind of algorithm in a short manner. The most important part is in here, as I said earlier, idea is very simple to beat a cap theorem, but implementation requires much more mathematical backgrounds. I can show you in here. During the speed layer processing, all required traffic goes to the speed layer. it requires responds most recent data from its database, its memory, from indexes. But at the same time, batch job, data in rest type of queries has to complete it and update the speed layer, serving layers when the speed layer resources before the speed layer resources goes off. So this we can model this is different time ranges and different processes. For the completion of area under the area under the curve for the A1 has to lower than the A2 and A3. Your algorithm, if it might be predictive, it might be PID-based controller, doesn't matter, has to concern this kind of constraint during all the time. You will have a very easy inequality. Area under the 1 has to be lower than the area under the 2 because of the fast transition. Our current solution requires currently 10 or 5 software-defined radios, which geographically located different locations. For example, Ankara Esenboğa Airport, for example, İzmir Adnan Menderes Airport, or this kind of area. Again, I say the devices are very cheap, $5. You can easily put or install it. These are also brings another kind of problem because even different kind of locations to the same plane or air vehicle has sent signal around, and 2 or 3 of your software-defined of radios receive the same signal. You should add some fusion algorithm to detect these tracks coming from the different software-defined radios represents a single airplane. So this can be done in speed layer and batch layer all together. And when the information received from the airplane, these processes are used for speed layer, batch layer, and serving layer. We developed an UI-based, graphical user-based architecture, which is called SciFly. I will show the UI side of it. And the main problem is currently in the literature there is not any kind of measurement system in the big data frameworks. Everybody offers some kind of databases or data products, but especially collision avoidance system or collision modeling system, you have to be very certain about what you did, because it prevents and cause death in the air or other problems. So you should test and monitor every single record in the very huge amount of data. So we developed this kind of system and start with the 5 remote software defined radio and improve it currently 81 because this system is attract Turkish Airlines attention and started to use their operations center. We have to test their accuracy. So we proposed a solution for it. These are the some snapshots from the SciFly system. Data comes from nearly, for this work, 5 different software-defined radio, different locations. Our algorithm understands these are the same tracks, same planes, same ground vehicles, and classifies and applies some complicated type of collision avoidance system, which comes from the game domain. Because you know, computer games are very popular and completely use this kind of application algorithms. This is the some visualization part of the system. You can see some part of the Turkey's airfield, air bases around, and left part of here, left part of the lower left part of the system shows you an heat map. When the plane goes much more time, use the same path, you can exactly find out the dense areas. Also shows you what kind of messages currently, what number of air vehicles you detected. Also, during this type of operation, we measured our Lambda architecture's processing speed. For example, green one is our speed layer. The batch layer, as you know, data is improved and processing time directly improved by using this kind of data under full load condition. Every time, as I mentioned earlier, area 1, we keep sure about area 1. The area 1 has to be lower than the area 2. And another screenshot, and up to this one, 525 gigabytes per second data is processing by using the system. And also, we can directly find what companies or what airlines, what countries that air vehicles are comes from or passing through your airspace, and most importantly, the companies that airplane produced by that company. These unknown air tracks are military aircrafts. By the way, if you dig in, you can exactly find out what kind of military aircraft. You can directly find it out. But we posted that now unknown. This is for the Esenboğa analysis, Esenboğa airport analysis. When the this is air traffic, and in that day, that traffic directs from this trajectory, and we will have some gap in here. We lost connection because of the geographical properties. We can do analysis or improve that kind of signal. And we tested very high computation analytic queries. Minimum distance, maximum aircraft speed, maximum altitude, average number of unique aircraft, and minimum aircraft distance, which is the horizon distance between software-defined radios and the aircrafts. This is very high and complicated calculation for a query. This is the best chance of measuring the complexity. According to our, we use a different kind of hardcore test cases. Normal conditions, increasing data rate, which simulates the airplanes passing through your airspace, is improved instantly. Decreased and instant data increase and decrease. Your system has to respond very well. Delayed data and repetitive data. These are the most bad situations you can write. Even 500 gigabytes per second data, our latency has always been lower than the minimal expected conditions. It provides the necessary conditions, and just using the two different kind of analysis window, especially the late data, can be easily tolerated at the next cycle and complete itself as expected. The system and testing methodology is shown here, used for can be used for real world problems to analyze the data. Thank you for your attention. F10.